My name is Ciro, and I'm a technical evangelist at Unity. I work out of the Brighton office in the south of England. Technical evangelist is these weird people that go to conferences and they talk and talk and talk and talk, like now.
And my name is Alessia, and I'm a technical evangelist as well, same office as Ciro. And today we're going to talk about something that is very new within Unity. It's about 1 month old and not many people know about it, and it's machine learning agents. It's a way of implementing machine learning into Unity. So before starting with that, we're going to take a look at what machine learning is.
Can we ask how many people know about machine learning?
Okay.
And how many of you have tried to actually do something with machine learning? Okay.
So machine learning is an application of artificial intelligence that provides systems with the ability of making choices, and basically it begins with observations. So from observations, we observe the patterns in the data that we collect, that we provide to our systems, and the system will be able to automatically, without the help of human beings, to make the best decisions given this information. So the kind of machine learning that we're going to look at today is reinforcement learning. You can see that in green. This image, probably coupled with the name reinforcement learning, is going to give you an idea of what it is. Basically, we're going to give information to our system about what is right to do and what is wrong to do. So we're going to provide a positive reward in the case in which our system is doing what we want it to do, and a negative reward, so a punishment when it's doing something wrong. So we're not actually telling it what to do, but we're telling it how to do it. So it's basically like we have a dog and we're teaching it to sit, and if it does sit, we give it a biscuit, for example. So it won't understand our language, but it will understand, it will basically associate that reward to the action that it's doing. So to perform reinforcement learning, we are going to use neural networks. A neural network is a computer system modeled on the human brain and nervous system. So it's based on the concept of nodes or neurons, and these neurons are inside the neural networks. And some of them are connected to the outside environment. So those are the ones that receive all the input from the outside. And these are the input layers. And also the input nodes, and they are in the input layer. On the opposite side, we have the output layer with all the output nodes, and they store all the information on the rewards and on the punishment. And everything in between is in the layers. And that's where all the computation actually happens. Are fully connected, so that means that every node is connected to every node on the other layers. And for each one of these connections, we have weights. So weights means that we associate a value to each connection, and this value can either excite this connection or suppress it. So it can change the weight of this connection.
So when we talk about machine learning in Unity, as we said, we have our own solution, our own implementation, and it's called agents, machine learning agents. It's been launched like roughly 2 months ago through the blog. So if you go on the Unity blog, you will find the thing. It's a repository where you can get the code. And so how does the Unity specific implementation work? It works like this. So we have these agents that are the ones that are going to perform the training and eventually learn. And they need an environment, which is the green block. So the agent, it performs actions, the environment does things, the environment will react somehow, and there will be a change of state. So the environment changes its state, and then it feeds back the state to the agent, and it says like, this is what I am now, and together with it, some reward. And that's how the agent learns, and then the cycle repeats. The agent is going to act again. Initially, it will be random, so it will do like random action, random movements, and it will get some reward and start learning and then refine the training more and more in time. And this environment looks like this. So the environment is actually a Unity scene, classic Unity scene that you know, and everything is done through game objects. So the academy, the blue bar that you see at the bottom, is a game object with a component called academy, which holds all the parameters of the training. So resolution, the time scale, because we can run the training faster, so just general parameters. And then, so you have only one academy. And then you can have multiple brains. And the brains are other game objects with a brain component. And they connect to the academy, they get these parameters, and they start learning. And they can be of different types. You see internal, heuristic, and we have two external. And we're going to talk about what it means. And then finally we have the agents. And the agents can be as many as you want. You can have multiple agents that connect to the same brain, so the training goes faster, or you can have just one agent per brain, as you wish. I don't know if I told, but also the brains, they can be one, or you can have multiple, and we're going to see why. So the agents, they have the experience, they learn, they pass the information through the brains, and they learn, right? And the brain learns, really. So this is Unity. But then when we want to run the training, we need something else. We need some external thing. And so the Academy has this external communicator that passes information outside to an environment which is called in Python. And it's called TensorFlow. It's a thing provided by Google. So the information goes to this Python thing, which is actually going to perform the learning. So Python collects all the data, and then the neural network runs in there and starts building connections. And so, as you can see, only the external brains speak with the exterior. So this is how you configure the thing in Unity.
So to give some more context now, we're just going to take a look at some example projects. Those are really simple demos, so it's not anything complex for now. So one example is the 3D ball. The aim of this example of, we have an agent that is the platform, it's not the ball. And what we want to do is to allow the platform to not make the ball fall. So we need to change the rotation of the platform so that the ball never falls. So this is an example that you can see. This is about 30 seconds of training, and the ball basically never falls. The way we do this is we assign a small reward for every frame that the ball stays on top of the platform, and we give a stronger punishment when the ball falls. So with frames, it will understand what's right to do and what's wrong to do.
It's important to note here that the agent is the platform, and they are all contributing to the same brain. So the one brain that's learning from 12 platforms, right? So the training goes faster. And this is a classic in machine learning. You want more agents to work in parallel to speed up the training.
Another example is propellers. We have these different cubes, and they all need to float, so to stay in the air as long as possible. So what we do is we only give one input, which is how high it has to be in comparison to the platform. And what we do is we give a positive reinforcement for every frame that it stays floating, and we give a stronger negative punishment when it's touching the platform. So it works pretty much the same as the 3D ball example. This is a demo that I've made, and it's basically just telling the agent to push the crate outside of the platform. So it's kind of like a sumo game. And what we do here is we have a reward when the agent is getting closer to the crate, because we want it to be able to collide with the crate and to push it out. And also a reward when the crate is getting further from the center. Also, we give a negative reward when the agent falls outside of the arena. And the last example is bounce ball, and it's basically we want the agent to make the ball bounce on its head as long as possible for how many times, for the many times. And what we do is we give a reward for each frame that the ball is closer to the agent, and we give a negative reward for each frame that the ball is the furthest away.
This is the Maradona example. So just to make sure that you understand, there is no code in the example that is telling the agent how to move. The agent is moving randomly at the beginning, and then he learns that he has to be below the ball to juggle it. Because when the ball falls, bad. When the ball stays in the air, good. So he eventually learns that he has to move that way. And these are all these examples. There's no code that is telling the agent how to move or when to do it or how much. this mine? Yeah. So after all these little examples that we worked on, we were thinking, okay, can we use machine learning in a real game, or or is it only good for little example scenes? And so we embarked on creating a real game, which is still like a very small game, but at least it has some gameplay. And we called it roguelike. And it's basically a simple action game with this little character. So you play as the knight, you move around, and you have a very simple attack, which is like an area attack. And you have some enemies, which are green slimes. You can have more enemies, but we just implemented one type for now. And when we came up with this idea, we came up with a formula. So the formula was to have a simple action game, and we wanted all the entities to be agents. So for the player, we could have made a custom script, but we decided that we wanted the player to be an agent as well, which doesn't mean that the player is controlled by the machine learning. The player is controlled by me, but it follows the rules of the agents. So it speaks the same language, it has the same actions. So as you can see, we wanted to establish a common interaction language. If I can move left and right
and up and down, and I can attack, then the enemies can do exactly the same things. There's no difference in gameplay between. And that's good because then we can train the players, the enemies, and vice versa, or our enemies against enemies,
because they do the same. And the goal of the game is surviving while attacking other entities, so a classic action game. Setting up the training. How did we come up with the training procedure?
This is Alessia on the whiteboard. So first we were like high level designing the algorithm, right? So first, what are the game actions? And we said, let's keep it simple. Move left and right, move up and down, and attack. Just that, because we are also new to machine learning, so we wanted to start simple. And then what do you want the agent to learn? So we wanted the agent to approach the enemy, attack, but then if it's in danger, step away and recover health by healing, and then step forward again. And so to do that, you need to decide what's right or wrong. So, and that's basically deciding when, where, and how much reward to put in your algorithm. So the algorithm that we came up, I'm going to show you to you now. The first thing that I wanted to mention, though, is this thing, because this is a pretty important decision that you take while you're planning your machine learning. So you have these two spaces, discrete and continuous, and they can be used in your states and actions. The states is what the agent sees. The actions is what the agent does. You can do discrete actions, discrete states, or continuous action, continuous states. Discrete means that states or actions can only have one value at a time. So you only have one number that can be 0, can be 1, 2, or 3, and it's only going to be one value. And that describes the whole thing. So we use that for the actions. For instance, if you see the last line, our action can have 6 values. 0 means the agent stands still, 1 is moving up, 2 is moving down, 3 is left, 4 is right, and 5 is attack, which means that he cannot move and attack at the same time. And because of this, as you can see, I say it's easier, because the agents associate actions with rewards more easily. Because if they move, and if they get a penalty, they will know that the penalty came because they moved. There's no confusion. On the other hand, you have continuous, which is more values, and they can have a lot of, so more variables, and they can have a lot of different values. So you can have like different float numbers. And we use continuous for the states. So the last line, we pass a lot of states, because we wanted to keep an eye on many, many things at once. We couldn't use just one number. So we had to pass health, we want to pass if he can attack or not, if he has a target, the distance from the target, and these are all numbers. We can't just pass one integer, right? So we use the mix of both. And they influence a lot because, as I said, discrete is easier to work with, continuous is more confusing. You need to train the agent much more because he needs to start, making sense of all these numbers that he gets as states before he can actually learn. He's like a little kid that has a lot of inputs coming to him. So this is how the pseudo algorithm looks like. And I said agent step because the agent script has a function which is called the agent step that is going to be called every frame. So on the physics frame, on the physics update, the fixed update, the brain calls the agent step. And this is roughly how it looks like. We've broken it into movement and attack. So as you can see in the movement, we basically gave the base routine of if you're healthy, if your health is above 50% and you're moving closer, good, reward. If you're not healthy and you're moving away, good. So we influence the agents to start doing that autonomously. And then on the other hand, we have the attack. So whenever they provide an attack input, we say, if you can attack, then you attack. If you can't, then we punish you. And we can't, by you can't, I mean, because the agent has a 1 second cooldown. Because we didn't want the agent to attack like every frame. So we established this 1 second delay, and we say, you attack, and then for the following second, you have to do something else. And if you attack, I punish you. That's very simple. And then there is the healing routine, which is like a bit separate and has no reward associated. I'm not gonna lie, a bit of a spoiler. Since this beginning algorithm, it has changed quite a lot because you train the agents and you learn things yourself, and then you need to refine and refine and refine and train again and refine again. So we learned a lot of things in these 2 weeks that we worked on this demo. One thing is a bit of tips on rewards. So rewards, they can come in the agent step, but also in other functions. So you can put this reward anywhere. It's just a float value that you assign a value to. And it can be anywhere. So it can be also on collision enter, for instance. So imagine the agent collides with something, and you set the reward to -1. And then the brain is going to swipe through and go like, okay, what's the reward this frame? Every cycle, it collects the total reward. Then another thing we found out is that the agents will find a way to exploit the rewards. They're smart. They're fucking smart. Because you give them a reward, and they will find a way to get the reward. And they will base their whole logic around getting the reward. So they're very driven. For instance, we gave the reward to move towards the enemy. And what they found out is that if they move away, they can get the reward again. And so they started doing this, like on 1 frame, because that was enough. They didn't even need to attack, because they were getting like a lot of reward per frame. And they will do it. So you need to find then a way to, double check and make sure that they move further and closer to the enemy, not just move away and repeat the thing. So you will add like a lot of patches based on the observation after the training. And then every small detail influences the learning process. So for example, before we were giving the reward divided by the distance squared from the enemy, because we wanted to reward if it was closer. But this was a big mistake, because if the distance is squared, then as the agent is very far, it's divided by a high number, and then the reward is very small. So the agent goes like, why should I even move if I get like this very small reward? So it's really depending on the distance. So we just changed it to just a plain number, which worked better. So any detail will influence the final model.
So now we're going to take a look at the training scene. What we use it for is basically to decide where we're going to put the agent, and then to connect the agent or the multiple agents to the many different brains that we're using, and also to configure the academy. So let's take a look at the demo. Yep.
So can I add one thing? So here it's important to note that, as I said, the environment is a scene, but you don't need to use the same scene for the gameplay and the training. So we built this custom scene just for training.
So yeah, to connect to what Ciro was saying earlier, we're going to take a look at the academy. So we have all the different elements that Ciro was talking about. So we have an academy here, and this academy is going to have all the settings that will allow us to configure the training. For example, the time scale, which we can use to decide how fast our training is going to go. So if we set it to 100, for example, our training is going to go really, really fast, but we won't be able to see all of it. So when we're testing it at the beginning, we might want to have it at like 1, so that it goes in real time and we can see what our agent is actually doing. And inside the academy, we also have all the different brains. So we have a player brain. We can see brain type set to player. And then heuristic brain, which is a brain that is already scripted. So that means that the behavior of the agents that are associated to the heuristic brain is already decided, so it's not going to depend on the machine learning.
It's kind of like programming your own AI, basically.
Yep.
It's hard-coded.
And then we have our trained brain, which is the one that we are going to send to Python to perform the training. So we also decided to have different sizes for all the rooms because we wanted to put the agent in a situation where it can have many different views. So it's not going to move always the same direction because it's going to be in different situations. So it's going to have different rooms, different sizes. And additionally, our heuristic agents, so these ones, the heuristic slimes, have different settings associated to them. So for example, this one has attack damage 5, and another one is going to have 6. So we made them different so that the agent would never get used to one single setting. So here we want to use our trained brain to train it externally with Python. So we go to brain type, and we have to remember to set it to external. If we run play if we run our demo now in Unity, it's going to give us a runtime error because it's going to tell us, well, you're not giving me the external tool to train this with. So we need to do this in Python. So we learned quite a few things, as Ciro was saying. And one of the things that we learned from our training environments is that, as I said, we made different rooms of different sizes because it's good to have many different situations that run in parallel so that our agents can learn from each one of them. Another thing is using heuristic agents is really useful. You can think of it as, like when you're learning martial arts, for example, you're always training with a master. So you're training with someone who is an expert in what they're doing. So it's not someone who's learning with you. For example, you wouldn't want to train an agent against another agent that is learning at the same time because that wouldn't work. They wouldn't know what to do. Also, before you launch your final training, that might last up to, say, 1 hour, you want to make sure that there's no flaws in your logic. So this is not about compile time errors. It's kind of errors that anyone can make. So it's not about how good you are at programming. Because in machine learning, you can make wrong assumptions. We did it when we wrote our first algorithm, and then after we ran it a few times, we realized that there were many things that weren't working. And also, as I said, you can set the time scale to normal speed so that you can see what's happening in real time. So now we're going to build our game, and we're going to launch the training and see what happens. To do this, we first set the brain to external, as I already done. Then we build. And we send this build to the Python environment. We change all the hyperparameters, which are a set of parameters that will affect the training. And then we launch the training. So we have already set the brain type to external, so now we can just build. And we need to remember the name of the executable that we're building with. So in my case, it's called roguelike demo. So I have my build. What I want to do now is I open Python. I use Jupyter Notebook. What I want to do first is I navigate to the folder where I have my project. And then I open Jupyter Notebook, which is the Python IDE that I want to use. And I open this file. So what happens here is, in this first cell, I'm just importing what the libraries that I need. So I'm just going to run it. In the second cell, I have all my hyperparameters. And one of them is environment name. This is why I told you to remember the name of your build, because you're going to need to insert it exactly as it is. And also, we have different parameters that are the hyperparameters that we were talking about. And you don't really need to understand what they do, because there is a guide made by the machine learning team at Unity that tells you what you need to change according to what your agents are trying to do. So this is mainly, it mainly changes according to discrete or continuous states. So we just run these again. And then we load the environment. It's going to tell you Academy started successfully if it worked. and then you train the agent. So this is going to start our training. As I said, you're not going to see it training in real time, so it's going to go really, really slowly. You will be able to see only a few of the frames because, sorry, not slowly, it goes really fast, so you will only be able to see some of the frames. And now we can just leave it here to train and go back to the presentation.
Prendere il caricatore del cellulare del computer. Si sta caricando. So now that the build is training, there's only one thing left to do, which is observe it. So as Alessia said, you're not going to observe the scene because it runs very fast. We run it 100 times because we want to do something like the default parameters are something like 500,000 frames. And you don't want to look at all of them. So you need to go faster. And so you can observe the reward that the agents are getting. And then once you think it's stable, then you stop it. You export the model. And you import it back into Unity. And you set the brain to external. And then you press play. So just to show you what I mean, you see here these three values. They are the mean reward. So every 10,000 frames, Python collects the rewards and makes the mean, which is kind of like an average, and it spits it up here. And as you can see, they're negative, very negative for now. So the agents are doing something very wrong. They're probably dying like several times, or they're getting away from their opponent and stuff like that. But they will learn. So slowly, they will associate the isolated good reward with the action they did, and they will start performing the action again and again, and they learn, and that number will go up. So you see now it's minus 117, and it's going up slowly. Eventually it will become positive, and then it will become way higher as the agents learn more and more, and they learn how to get those rewards. So this is a terrible model for now, but we don't have time to train further. So you see it says saved model. So at this point I can basically stop the build, and you see the build is being closed. And here we have a bunch of debug information. Then we go down here, and we execute this last line, run. And you see the model gets exported just with these 50,000 cycles. It's a terrible model, I want to remind you. All right, so it has basically spit the model out, and then we can go to Finder. The windows are closed, I guess. Can we find it? Yep. So now we navigate back to the basically where the Python has saved this model, which is nothing else than a text file. So it's a text file with the extension of .bytes, and we need to bring it to Unity. So yeah, models, PPO, and you see these are like all the intermediate steps, and then you get this thing, which has the name of the build, .bytes. So we also want to go to our Unity asset folder, so we just go in here, and we go to the models, right-click, reveal in Finder. Of course, we get the window in another space, but we're very fast. So we bring it here, and we copy, and we paste the model in this folder. We go back to Unity, and we have it here. This is just a text file. So we then go to the academy, to the brain that we want to be controlled by machine learning, and finally we set it to internal, and here we connect the model that we just trained. We say use this model, and we press play. And the agents are terrible. So I'm the purple one, I can move around, but you see these guys are just doing random stuff because we didn't train them enough. We just ran 50,000 loops, 50,000 steps. So they don't know what they're doing. They're just producing like random inputs. They're moving randomly like this, and then sometimes they attack. So you see now, this is our training environment. You see the greenish, these ones, they are heuristic. So they just have an algorithm that does random things. And the agents are the green ones, and they look pretty helpless. And I'm the purple one. So as I said, similar language means that I can play as an agent, and I can possibly go near the agent and test what he does when I attack him. He's not very smart, he's just gonna attack like endlessly and possibly die. So these are not very smart. So what do we do? We train the model way more, like hours. And then we get something like this one. So if I go into the trained brain and I use this model instead that we trained back home, and we press play, we see something different. Look on the right side, which is probably the best. So that's me, and I can attack the agent. He fights back. Am I gonna die? And as he gets some damage, he starts moving away. You see? He doesn't follow me anymore. And now he's getting healed. He's getting his energy back, and then slowly he's gonna come back for another round. So now he has learned. So as you can see, nobody programmed him to go towards me or away from me, but he will do it because of the rewards that we gave him. And
so here we're just going to give you some key takeaways from this presentation. Some of them are on hyperparameters. So as I said, they're variables that affect your training. And one of them that is very useful during training is beta. Beta is basically how random the actions of your agents are going to be. So basically what it does is that the agent might just choose that one behavior is right, so it will just keep doing that, even if it gets just a bit of reward. While if you increase the beta, it's going to try other possibilities that might give it more rewards or maybe less, but it's going to try.
you can kind of see it as like the creativity of the agent. He's training and he gets creative and he tries new stuff. And maybe he finds a better strategy. So the beta, I think, higher, then he's going to try more things randomly.
Yep. And then we have batch size, buffer size, and hidden units. You don't really need to understand what they do, but you need to know that they have very different values depending on whether you're using discrete or continuous spaces. And everything about these values and also the wiki about machine learning is at this link on the Unity GitHub. So you can just take a look there and find all the guide that you need. Also, we have tips on physics. As Ciro said, agent step runs on fixed updates, so that's the physics update. So you need to remember that if you are using rigid body dot position, that won't change at the moment that you're actually changing it. So it won't get updated during the same frame, but at the next frame. So if you're giving a reward at that frame, just remember that the agent is not associating it at that moment, but at the next frame. So keep that in mind. And if you're also working with animations, which is what we were doing, and we made a mistake on this, you need to remember that you need to switch all the animations, especially if they have to do with the reward, so with the training. You need to switch them to animate physics so that they run at the physics frame, at the physics update, and not at the normal update. And also if you're using interpolation on the rigid body, so you don't want the rigid body to just completely teleport somewhere else, remember that rigid body dot position and rigid body dot move position behave differently. They are two very different things. And to finish, we made a machine learning helper. Ciro made it, and it's something that helps you to automate the process of getting the brain from your environment and then exporting it onto Python and then putting it back, because it's something that you need to repeat many, many times, and you can make your life easier and just use this instead. You can make your own, or I'm sure we're gonna make these available.
Yeah, maybe. So yeah, it's just a little window, you know, because you're doing this process all the time, like continuously. It can be tedious to always like select the brain and set it to external, run the build, and then you set it back to internal, assign the thing. I made this little script which like finds the brain, and then if you hit this button, it just builds. And then once you've done training, you come back into Unity and you press 1. Well, it's not in the right directory, but you press 1, 2, and you press play, and then you can run the training, observe, and if it doesn't work, you press this button again, and you go back into the Python, and you run another training. So because the thing is very tedious, because it's very repetitive, you want to automate this step and make your life easier to save some time on that part. One last demo. So we talked about the game. So where is the game? If this is the training scene, we said that we have another scene which is actually the game. So don't expect like huge things. It's not a huge game. But this is the game. In this scene, we can actually see the thing in motion. And we're also using some other Unity features that Unity released recently, like the tile mapper. So this is using tile maps for the pixel art. And then it's also using Cinemachine. So each one of these little rooms that you see here in the scene view, they have a camera, they have a shot. And then we move between them with Cinemachine. So let me double check that everything is in order. You see, even here we have the academy, we have the player brain for my player, and we have the trained brain. And we need to make sure that here there's the best model ever, it says. I can zoom. Yeah, so this is fine. The trained brain is internal, so I can press play. Let's see what it looks like. And so again, this is me. It's still a machine learning agent, but it's controlled by me. So it has a brain that is not learning much. And I can attack with the same rules. And then as I move here, I meet a trained agent, which is going to come closer to me, and then we can attack each other. And if I let it live for a while, it's going to step away and then heal, and then it's going to come back. Then we can fight again. Of course, this is a very weak agent. Yeah, very weak enemy. And then, yeah, then you can go around. You have this room, which is kind of useless. It's one of those things that you end up putting in the build anyway. And then you have bigger rooms. So here you see Cinemachine at work, like these camera movements are all Cinemachine. And then you have all the agents. Still, they're not a big of a challenge, but if they were. They have a very low range of searching for the target, so only the ones that are really near me will come towards me. But then once they get the target, they're approaching the enemy and they're fighting and they're going away. Is all powered by machine learning. And that's it. That's a really simple game, as I said. Like the interesting thing, we are gonna give you the code if you want, so you can get the source code for this game and you can play around with it. You can train your agents yourself. You can change the algorithm if you want. You can play around and try to add more actions. It's not easy, but you can do that.
So the API is all available online. You don't need to code your own brain and academy and agent. Everything is already online, and you just need to extend it.
Yeah, you can play around with it. So okay, so what are the next steps? We showed you a very small demo. Maybe you're thinking, okay, but what can I do with this? Can I actually make a bigger game? And we're not going to lie that the process of training is complicated, and it can lead to very good results, but it's really hard to how can I say, to handle. There's so many things that can go wrong when you train. If you just give the smallest bad reward, everything changes. And so my idea is that maybe you want to mix some trained AI done with machine learning with some heuristic AI. So an AI that you make, you mix it with some machine learning part. So there's an agent, like an enemy, that can do complicated stuff, and part of it is powered by machine learning and part of it is powered by you, hard-coded. So for instance, you can handle hard-coded position in the world and, you know, I don't know, locomotion and stuff like that. And then once the enemy gets in range with the player, then you switch to the machine learning behavior and you use that to provide like an interesting challenge. And then once this steps away, you just switch back to the hard-coded behavior. So you can mix machine learning with other techniques for more complex games to obtain the final behavior. And then another thing that people have been asking is, okay, so how do we do machine learning that learns from the player? Because we've seen machine learning from himself, right? From like self-experience. So how does it learn from the player? And right now there's no solution like that that works with Unity. it's coming. So is that thing called imitation learning, which is going to provide a way to train the agents while the player plays. Because right now you run the training at like 100 times speed. That's impossible. Blah blah blah. Imitation learning is going to extend on this thing to provide that functionality. But what I think is what you could do is if you have a game that's online, or even if it's an offline game, but you are able to gather data from your players, then you can come up with a system that uses machine learning, train it yourself, then put the game online somehow, maybe with a beta, a closed beta or an open beta, and you gather the information from the players, which is not just the moves that they make in the game, but is more like the strategies that they play. So you come up with some solution to read the strategies, and then you train the agents yourself against these strategies. So imagine recording what I just did in the demo and distilling it into a strategy and then training the agents again against that strategy. And they refine and they become better and kind of bulletproof against that strategy. So they learn to counter that strategy. If you have like 2, 3, 15 different strategies, then they're going to become way better. And so, and then you can put this stuff online again for the players to play. So they get like a refined version of the game every time you update the model inside it. And that's everything. So, spasibo from me.
Спасибо.